The plan today is as follows. My plan was just basically to go through a bunch of, continue to go through the old exams. I'm going to finish going through the final from last year, and then I could go through the practice final. I think in the math lab review sessions, typically they go through the official practice exam. So I was not going to do that one just because I'm assuming that's the one that they will cover today. So for those of you who can attend the official math lab one, I'll kind of try and cover different material than I think that they're going to be covering then. So any questions or things that you guys want to see today specifically, or should we just dive in?
Could we talk about similarity between matrices and some of those other decompositions that aren't the singular value decomposition?
Like, do you mean like the spectral decomposition type thing and diagonalization? Yeah. Okay. Yeah. So to answer your first question, similarity is just this property. We say that the matrix A is similar to the matrix B. What that means is that you can find another matrix P, so that P times B times P inverse is equal to the matrix A. Now we kind of defined this, and we didn't talk too much about it. It was kind of only like a quarter of a class we talked about it. But the idea is that whenever two matrices are similar, they'll always have the same characteristic polynomial. Okay, so A and B in this case will have the same characteristic polynomial. They'll have the same eigenvalues, but in general they'll have different eigenvectors. Okay, so that's kind of the key thing you want to know about similar matrices, is that they share some properties in common. The same characteristic polynomial, the same eigenvalues. They will have the same determinant as well. I guess that's another thing we can say. But in general, the eigenvectors will be different. Okay. Now that's about all we said in terms of what similarity means in general. The instance that we kind of focused on, I guess I can bring up a different page here, was this here. Let's see. So the thing that we really cared about is, well, what happens if your matrix is similar to a diagonal matrix? Okay. And that's kind of the case where we actually spent some time talking about that. So the situation we really cared about is when D was a diagonal matrix. Okay, and so if I were to give you two matrices A and B, and if I were to ask whether they're similar, that can kind of be a tricky thing to answer. But a bit of an easier question is if I give you the matrix A and I ask you if it's similar to a diagonal matrix, and that's that process of diagonalization that we saw. Is that kind of what you were asking about, Matt?
Yeah, that's what I was asking about.
Okay.
So B or the matrix D is always going to be diagonal. Is that right?
Yeah, I mean, in general, no. I mean, you could talk about similarity where B is not diagonal, but for everything we talk about, generally that was the case. Yeah.
Okay.
Like you definitely could think about similar matrices that are not diagonal, but we didn't spend really any time on that. So
awesome, thank you.
Okay, and then you asked about the other decompositions, like spectral decomposition, things like that.
Yeah.
Maybe I think we have an example coming up of like a orthogonal diagonalization, and then maybe there we'll talk a little bit more about that.
Awesome.
That's cool.
Thank you.
Okay. If I forget, which I am, quite possible might happen, just bring it up again. I always do this where I'll say, oh, we're going to get to that in a bit, and then sometimes I forget to actually come back to it. So if that happens, I'm not purposely trying to dodge your question. It's just I forgot. So feel free to remind me. All right, so let's talk about any other questions before we jump into the examples?
There's a bunch in the chat, Dr. Hughes.
Are there? Okay, let's see. Yeah, when I have the videos up, which I like to do, I can't always see. Okay, so diagonalization and finding related vectors. Can we go over more conceptual questions? Is there a key for the free response from last year's final? just has the answers to the multiple choice. Okay. Yeah, I don't know that I have a key, but we can go over the free response right now if that's cool, Taylor. Like we'll continue working. So some people ask for conceptual questions. Some people want sort of the answers to the free response. Probably what we'll do is we'll just continue going over these multiple choice questions. These are kind of more, some of these are more conceptual, and then we'll do some of the free response, and then we'll do another exam. So I think hopefully we'll get to kind of all the things you guys want to see, conceptual questions and the free response. Is that cool with everyone? Yeah, sure. Okay. So I think if we just kind of work through, we'll see kind of a nice mix of examples. So hopefully that'll answer most of your questions. But again, if something comes up in the meantime, feel free to bring it up. So this question here is asking, question 11, and again, this is on last semester's final. Which of the following matrices are orthogonally diagonalizable? Okay. Now, remember, if you want to determine whether a matrix is diagonalizable, it comes down to asking whether the algebraic multiplicity of every eigenvalue is equal to the geometric multiplicity. In other words, the number of eigenvectors you get. Okay. So if this were just asking, if this question were just asking which of the following matrices are diagonalizable, then there might be some work involved in finding eigenvalues, finding eigenvectors, and making sure that those multiplicities match. Is our life made any easier or more difficult by the fact that we're asking for orthogonal diagonalization?
Easier.
Why is it easier, Hunter?
I think they just need to be symmetric.
Yeah, because remember, orthogonally diagonalizable, really, that just means symmetric, right? Every symmetric matrix is orthogonally diagonalizable and vice versa. So we really don't even have to look for eigenvalues and eigenvectors here. We just have to determine which matrices are symmetric. And looking through it, we see the first one definitely is symmetric. The second one is not. The third one is symmetric. The fourth one is symmetric as well. Fifth one is not. And the sixth one is not symmetric either. Okay. So remember, we're just checking, we're looking at the matrix, and we want to check whether the transpose is equal to the matrix itself. Any questions on that one? Okay, that's a classic question. Really, it just comes down to, do you remember the fact that orthogonal diagonalizability is equal to the same thing as the matrix being symmetric? Okay. Let's compute the characteristic polynomial of this matrix here. So this is kind of a straightforward computation. Remember, the characteristic polynomial is, if we call this matrix, say, call it B, the characteristic polynomial is just the determinant of B minus lambda times I. So we're just looking at this determinant here. Hopefully we were kind last semester and we gave us a nice one that's going to work out nicely. Any preferences on how we do this?
The vertical down the left column would be easiest.
Yeah, we could do vertical around the left column. I actually see a row operation in mind that would make our lives even easier. Does anyone see it? So I definitely could do cofactor expansion along here or cofactor expansion along here. There's a couple of zeros we could take advantage of, but I'm actually going to do a sneaky row operation here. I'm going to do lambda. I'm going to take row 2, and I'm going to add on lambda times row 1. Okay. So by doing that, I'm going to take this row, multiply it by lambda. Oh, does that make my life easier? No, it doesn't really, does it? Because I'm going to get rid of this lambda, but I'm still going to have a lambda there, lambda squared there. Yeah. I don't think that really makes anything easier. Okay, so forget I said that. And yeah, I don't really see any single row operation that's going to help us too much. So let's just go ahead and let's just do cofactor expansion. So I think Matt said cofactor expansion along the first column. So we'll do the negative lambda. This is in a positive spot, so it just stays. It's just going to stay negative lambda times the determinant of the matrix I get by crossing out the first row and first column. So that's minus lambda 1 minus 5, 4 minus lambda. And then we'll do 0 gives us nothing. Then we get a 2. Again, that's in a positive spot. So it's plus 2 times the determinant of 1, 0 minus lambda 1. So I'm just going to take these determinants. Okay, so I think we will get minus lambda cubed minus 8 lambda squared minus 5 lambda plus 2 lambda. And so if I
4 lambda squared, I think.
Isn't the determinant on the right just going to be the end result's just going to be 2? Because you have 1 times 1.
Oh, that's 1. A 0. That's a big fat 0, right? I forgot that 0 times negative lambda is not negative lambda. That's a fact we all know, right? 0 times something is 0, typically.
I'll take it on faith.
Okay, yeah, and I can prove that later for any of you who haven't seen that result before. It's a nice result. So you get negative lambda cubed. Oh yeah, I don't know where the 2 came from in my head. What was I doing? Minus 4 lambda squared minus 5 lambda plus 2. Is this one of the options we have? I think it should be. I think it's this.
Second from the bottom.
Is that second from the bottom there? Yeah, there we go. Awesome. Okay. So that was
one more down.
Oh, one more down? Oh yeah, I got the wrong. No, but then that's a plus 4.
But on the top one, the one you have is minus 2 at the end.
Yeah, this one is minus 2, but this one has a plus 4 instead of a minus 4.
None of the above.
When you take the determinant, you're going to get minus lambda times 4 minus lambda. So it's going to be lambda squared minus 4 lambda plus 5. And then you're multiplying it by another negative lambda. So that's going to flip the sign of it.
Oh, yeah, it's a minus 4. Sorry. I thought I took care of the sign already. Yeah. Okay, so this one looks okay then.
Yes, sir.
Okay, and that's just your daily reminder that it's easy to make a lot of algebra mistakes on these. So take your time, check your work. If you have time, you could always, of course, do a cofactor expansion along a different row or a different column, and that would give you a very good independent sort of check to make sure you've done things correctly. So definitely take your time. Lots of ways to make mistakes on these. Any questions on this calculation?
Can you remind us what doing different row operations does to the determinant?
Sure. So if you have a matrix, say you have a matrix, I'll just write, just a quick matrix here: 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember, if you say you take a multiple of one row and add it to another row. So in this example, say I took the first row, I multiplied it by 2, and I added it to the third row. That would give me 9, 12, 15 on the third row. Okay. So if I do that, if I do like say row 3 plus 2 times row 1, that doesn't change the determinant at all. Okay. So you can add a multiple of one row to another. It doesn't change the determinant. If I were to take, say I took a matrix, I'm going to switch to the vertical bar notation. Say I took a matrix and I had like a 2, 2, 8, 1, 7, 1, 3, 3, 24. Whenever you have a row that has like a factor, you can pull that factor out. So the the way that it's said in, I think, the notes is if you multiply one row by a scalar, it changes the determinant by that factor. But the way that I always have it in my mind, I think the more useful way to think of it is that whenever you have a row where you can pull out a scalar, you can do that, and it just changes the value of the determinant by that scalar. So it kind of looks like what you're doing is you're factoring it out. And that's kind of the way that I think about it. It's easier to kind of keep track of it in my mind. So in this example, we could pull out a 2 from the first row, and that just gives us a 2 in front. We could also pull out a 3 from the third row, and that would then give us like a 6 in front, right? When we pull that 3 out as well. And the last thing we can do is we can swap 2 rows. And if you swap 2 rows, what it does is it changes the determinant by a sign, okay? All right, is that okay? Okay, now I also think I told you, I showed you in an example a while back that you can also do column operations. So if I swap 2 columns, it changes it by a sign. If I add a multiple of one column to another, it doesn't change it. So everything you can say about row operations, you can also say about column operations. So keep that in mind. All right. Oh, hey. It was on the stairs. It was on this. Oh, it's on the cans up there. Sorry, working from home. Yeah. So, okay. Any other questions before we do another example? No. All right. So let's look at this next one. This is more of a conceptual one. This one here. Just going to clear up some space here. Let A be a 3 by 3 real matrix with A transpose equals A and eigenvalues 2, 2, negative 1 with eigenvectors v1, v2, and v3 respectively. Which of the following must be true? Okay, so let's see what we can conclude from the information we're given. Okay, so let's kind of highlight some of the facts we know. So first of all, we know that A is a 3 by 3 matrix. Okay. The other fact that's kind of useful is that A transpose is equal to A. What's another way of saying A transpose is A?
Symmetric.
Yeah, A is symmetric, right? Now, as soon as we recognize that it's symmetric, now we should be thinking, okay, there's a few facts we know about symmetric matrices, right? We know that they're orthogonally diagonalizable. We know that vectors from different eigenspaces have to be orthogonal to each other. And a few other little facts we might know like that. So we should kind of be clued into that spectral theorem that we saw. And we're probably gonna be asked about a few facts like this. And then of course, we're told what the eigenvalues are and we're told what the eigenvectors are, okay? So let's see which ones must be true. The first one, A is a diagonal matrix. A is diagonal. Does that have to be true?
No.
Yeah, no, it definitely doesn't. So for example, you know, I could give you a symmetric matrix that you know, definitely isn't diagonal. This would be an example, okay? So not every symmetric matrices don't have to be diagonal. So this one is false. V1 dot V2 is equal to 0. Does that have to be true? Do the eigenvectors V1 and V2 have to be orthogonal?
Yes.
No.
Why not?
I
They
think
come from the same eigenvalue.
from the same eigenvalue. They're not guaranteed to be orthogonal to each other.
Yeah, so it doesn't actually say anything. It just says V1 and V2 are eigenvectors for 2 and 2. So they're both eigenvectors for the same eigenvalue. And for all we know, they actually could be this exact same vector, right? We don't actually even know that they have to be different. So we actually don't know that they're orthogonal. And that was kind of thrown in there to trick you, I think, okay? So if they were from different eigenvalues, they'd have to be orthogonal. But in this case, we don't tell you they're from different eigenvalues, so they don't have to be orthogonal. What about A being invertible?
It doesn't have to be.
Careful. So if you just knew that the matrix was symmetric, then you're right. You wouldn't know that it has to be invertible. Okay, but we're given a little bit extra information. We're told what the eigenvalues are. Do the eigenvalues tell us anything about whether the matrix is invertible or not?
Yeah, they do.
What do they tell us?
that it is?
It is, yeah. So remember, a matrix is not invertible. Okay, if and only if lambda equals 0 is an eigenvalue. Okay, so one way of telling whether a matrix is invertible or not is by looking at the eigenvalues. And if 0 is not an eigenvalue, then you know that if 0 is not an eigenvalue, then you know it has to be invertible. And vice versa, if 0 is an eigenvalue, you know that it's not invertible. So that having 0 as an eigenvalue is equivalent to saying that the matrix is not invertible. So in this case, we know that 0 is not an eigenvalue. Therefore, we know that the matrix does have to be invertible. And do you guys remember why 0 being an eigenvalue tells us it's not invertible? Well, if 0 is an eigenvalue, then that means that there is some non-zero vector x which satisfies this equation, right? And if there's a non-zero vector x that satisfies that equation, it really means that there's some vector x that lives in the null space, some non-trivial vector that lives in the null space, which means that the matrix has free variables, it doesn't have a pivot in every column, yada, 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 okay? Everyone okay with that? So zero not being an eigenvalue tells us that it is invertible. Part 4, A is orthogonal. Do we know that A has to be an orthogonal matrix? No.
Can I back up and ask a quick question?
Yeah, certainly.
If you have a matrix that you know is non-invertible, does that guarantee that lambda equals 0 is an eigenvalue?
Yes. Yeah. Yeah, and again, you know, one way you can think of it is if the matrix is not invertible, then, I mean, there's a few ways to kind of get there, but if a matrix is not invertible, that means that when you row reduce it down, you're not going to get the identity matrix, which means that you don't have a pivot in every row and every column. Therefore, you have to have free.
Which gives you lambda equals 0.
Yeah, well, yeah. It basically tells you that there is, you know, not having a pivot in every column tells you there's a non-trivial vector x that satisfies this equation. And if there's a non-trivial vector that satisfies that equation, then really that's the same thing as saying there's a non-trivial vector x that satisfies this equation. So, is that okay, Joshua?
Yeah, got it. Thanks.
Awesome. Okay. So A is orthogonal. What does orthogonal mean? Remember, it just means that the matrix has orthonormal columns. Okay. Just going to clear some of this up. So remember, orthogonal tells me that A has orthonormal columns. And we definitely, just by saying that our matrix is symmetric, doesn't tell us that it has to have orthonormal columns, okay? And actually, how do we know that this matrix isn't orthogonal? We actually know that it, not only doesn't it have to be orthogonal, but we actually know that it can't be orthogonal. What piece of information tells us that it's not orthogonal?
The eigenvalues are not equal to the absolute value of 1.
Yeah, exactly. The eigenvalues here, remember, if it is orthogonal, then the eigenvalues all have to be equal to 1 in absolute value. In this case, we have eigenvalues that are definitely not equal to 1 in absolute value, and therefore it's definitely not orthogonal. Okay.
Is that each eigenvalue has to be equal to absolute value of 1, or just they all multiplied together have to be equal to absolute value of 1?
Each of them has to be equal to 1 in absolute value. So for example, you could have, say, 1, -1, -1, and 1 be your eigenvalues, or whatever. But all the eigenvalues really have to be like plus or minus 1. And actually, technically speaking, it is possible to get things like complex numbers as your eigenvalues. And so we're kind of ignoring complex numbers in this course, but you should know if you see eigenvectors and eigenvalues later on, you know, it is possible to get something like 1 over rad 2 plus I times 1 over rad 2. Like, you know, you could get complex numbers that have absolute value equal to 1 as well, but we don't worry about those in this class, so don't worry about it. For our purposes, you can kind of think of the eigenvalues as being plus or minus 1.
Okay, sounds good.
The next.
Can I hop in again?
Sure.
So we know that for an orthogonal matrix, that all these properties are true, like about its inverse equals its transpose, etc. All these different properties. Is that also true for an orthogonally diagonalizable matrix?
No, yeah, no. So that the words orthogonal matrix and orthogonally diagonalizable, I mean, they're similar enough. You might think that they have sort of something to do with each other, and they're related in some way, but it's not. All these nice facts about orthogonal matrices aren't true about necessarily about orthogonally diagonalizable ones.
Okay.
It's a good thing to clarify, yeah. All right. So let's look now at the next option. There is an orthogonal matrix Q, so that Q times Q transpose AQ is diagonal. So that's like saying there's an orthogonal matrix Q, so that Q transpose AQ is diagonal. Is that going to be true for a symmetric matrix? Well, what does this kind of look like? This kind of looks like diagonalizability, right? Except it's just kind of rearranged a bit. If we multiplied both sides by Q, okay, well, Q times Q transpose, because our matrix was orthogonal, Q transpose is equal to the inverse of Q, and so that this side cancels, and we just get AQ equals QD. And if we multiply the right-hand side by Q transpose, the same thing's going to happen. It's going to cancel with the Q. And so we can kind of rearrange our equation using the fact that Q transpose is equal to Q inverse. We can kind of rearrange our equation to look like this. Is this going to be true about the matrix A?
Yes.
Yeah, because this is just saying that our matrix is orthogonally diagonalizable. And remember, symmetric matrices are orthogonally diagonalizable always. The next option is v1 dot v3 is equal to 0. Does this have to be true?
Yes.
Yes, this one is true because v1 and v3 are eigenvectors from different eigenvalues, okay? And remember, for symmetric matrices, eigenvalues that come from different eigenvectors that come from different eigenvalues are orthogonal, okay? So v1 and v3 will be orthogonal. And the last one is the geometric multiplicity of lambda equals 2 is 2. Why does that one have to be true or false?
It doesn't have to be true because v1 and v2, like we said earlier, could be the same vector. So it just have a geometric multiplicity of 1.
Okay, good. That's a good point. So v1 and v2 might not be linearly independent, right? So maybe these aren't the vectors that you want in order to diagonalize your matrix. But because our matrix is symmetric, we know that it's orthogonally diagonalizable, right? Okay. And remember, if a matrix is diagonalizable, that tells you that the algebraic multiplicity of every eigenvalue lambda is always equal to the geometric multiplicity of lambda. Okay, so because our matrix is symmetric, we know that it can be diagonalized orthogonally, but the orthogonal part isn't necessary. But so it's diagonalizable, and if a matrix is diagonalizable, then you know that every algebraic multiplicity is equal to every geometric multiplicity. And so therefore, because this eigenvalue has algebraic multiplicity 2, it has to have geometric multiplicity 2 as well. Okay. So, but Matt's right. The two vectors we got here might not be linearly independent, but we know that when we go about looking for eigenvectors, we will find linearly independent ones. Okay, it just might so happen that these two that they gave us aren't the two that are linearly independent. Okay. Questions on this? This was a conceptual one, so could be lots of questions here. No, you guys got it locked down.
That's good to know. Good to remember.
Yeah, I mean, there's lots of ways. I mean, these questions can be kind of subtly worded, so it's worth reading them pretty carefully.
Hey, Dr. Hughes.
Yeah, go ahead.
Sorry, I actually do have a quick question. Is
Sure.
it possible that we can go over like the different facts that we know if a matrix is orthogonally diagonalizable?
Sure. Yeah, I can flash those up on the screen right here. They were from chapter 5. And oops, I'm scrolling the wrong way, I guess here. Change the scrolling to vertical. This was Gram-Schmidt stuff. Yeah, so these were kind of summarized in 2 theorems at the very end of section 5.1. So the first theorem was basically if you're the first theorem that we saw about orthogonal matrices was basically if you have an orthogonal matrix, then it is a matrix that preserves the length and angles of vectors. Okay, so normally we think of linear transformations, and maybe what happens is they, when we apply a linear transformation, maybe they like, rotate vectors, and they like maybe 2 vectors that were orthogonal to each other, now they sort of get squished together. That can happen with a regular matrix. But what this theorem is telling us for an orthogonal matrix, if you have sort of 2 vectors and the angle between them is 30 degrees, then when you multiply them by the matrix, the angle between them will still be 30 degrees, okay? So orthogonal matrices preserve angles of vectors. They also preserve the length of vectors. So if my vector has length 4 and I multiply it by an orthogonal matrix, the new vector will also have length 4, okay? And that's kind of because the reason that kind of happens is because orthogonal matrices preserve the dot product, okay? And the way that we measure, the way that we think about angles and the way that we think about length in vectors is using the dot product. So that's kind of where that comes from. Is that first theorem kind of okay, Sarah?
Yes, thank you.
Okay. The second theorem is a few more, has a few more of these other facts that we saw. So if U is an orthogonal matrix, then some of the facts we talked about, well, the determinant of an orthogonal matrix has to be plus or minus 1. The eigenvalues of an orthogonal matrix have to equal 1 in absolute value. So for our purposes, you can think of that as just saying they have to be plus or minus 1. They have to have orthonormal rows. So that might be a bit surprising. We know that orthogonal matrices have orthonormal columns, but it turns out that the rows also have to be orthonormal, and that just kind of happens. You kind of get that for free as long as the columns are orthonormal. U has orthonormal columns. That's also sort of something we know. And then also, if U is orthogonal, then the transpose is also an orthogonal matrix. So when you take the transpose, you're also going to get a matrix with orthonormal columns. So I think these were kind of the key facts that that we kind of had to keep in mind. Is that okay, Sarah, as a brief review of those things?
Yes, thank you.
All right.
Quick question.
Yes.
Can you remind us what orthonormal means? I just had it in my mind.
So orthonormal. So if I give you a set of vectors, say V1, V2, and V3, they're orthonormal. What that means is it means that they're all orthogonal to each other. So V1.V2 is 0, V1.V3 is 0, and so on. Okay, so all of the dot products are equal to 0, so they're all orthogonal to each other. And then the other thing is that the length of every vector, so the length of V1, which is just equal to the square root of V1.V1, the length of V1 has to be equal to 1. The length of V2 has to be equal to 1. So they all have to be unit vectors. Okay. So the ortho part tells you that they're orthogonal. They all meet at 90 degrees. The normal part tells you that they're all unit length. Is that all right, Maddie?
Thank you. Yes, thank you.
All right. So here are some sort of short answer questions. Some of them are just kind of straightforward computational, but some of them will be a little bit more conceptual. so in the first one, we're given a subspace of R4, and it's spanned by these two vectors here. So that it's spanned by V1 and V2. Okay. Now, let's see. So W is spanned by these two vectors, and we want to find a basis for W perp. Okay. How do we find a basis for an orthogonal complement? If we have vectors that span the subspace, how do we find a basis for the orthogonal complement of it? So there's a little trick involved. We've seen it a couple times, and it's a valuable trick. So I would recommend you kind of understand this. So the trick is really our subspace W. I'm just going to write it out a little bit like this. So subspace W is equal to the span of these two vectors. They wrote them as row vectors with a transpose there. That's just because they were trying to save space. I'm going to write them as column vectors. Okay. So W is equal to the span of these two vectors. Okay. Now the trick is I don't know how to find a basis for an orthogonal complement of any old vector space or any old subspace. The only thing I know how to find orthogonal complements of are like things like row spaces and column spaces, because we know that the orthogonal complement of a row space is a null space. So the trick that I'm going to do is I'm going to create a new matrix, and this matrix is just going to be the matrix I get by plugging in the vectors V1 and V2 as the rows. Okay. So I've written down this matrix A, and now if I look at the row space of this matrix, that's just the space spanned by this row and this row, right? But the space spanned by those two rows is really just the space W. So what I've done is I've built a matrix A whose row space is equal to the subspace W that I care about. Okay. Now, why is that a useful observation? Well, it's because I know that the orthogonal complement of the row space, because if W is equal to row A, okay, then the orthogonal complement of W is equal to the orthogonal complement of the row space. And what is the orthogonal complement of a row space? Say it with me.
Null space.
Yeah, null space. Okay, so this is a trick, but we do it again and again. We've done it. It shows up. It's a trick that can help you with the SVD. It's a trick that can help you in finding a basis of a orthogonal complement. And that trick is that you have some subspace. You don't really know much about it, but you build a matrix whose rows are the vectors that span the subspace. And now all of a sudden, the thing that you care about is a row space. And we kind of are more used to dealing with things like row spaces, okay? Any questions on just kind of the outline of that trick that we've done?
So A just equals W transpose?
Well, so W is a subspace and A is a matrix. So they're kind of different objects altogether, right? But we kind of, you know, the way that we kind of built A is we took the vectors that spanned W, we turned them on their sides, and we made them the rows of a matrix.
If W was a matrix, it would just be the transpose. But since it's not a matrix, we don't say that. Sorry, yeah, I didn't. Was that you, Trenton? I didn't quite hear the first part. So like if W was a matrix, it's just the transpose, but we have to be careful to distinguish that it's not a matrix because it's a subspace. Yeah, exactly. Yeah. If it were a matrix, that's essentially what it would be. Yeah.
Hey, Professor Hughes.
Yeah, go ahead.
Could you remind me why the row space of A transpose is equal to the null space?
I can show you that if you remind. Yeah, let's do that right. I was gonna say remind me, but let's do that right now, because I can guarantee I'll forget. Okay. It's a fact that we saw right here. Okay. So essentially we kind of proved this fact by an example. We didn't actually like rigorously proved it, but we just kind of showed an example to see why it was true. Remember here, I gave you the matrix A, here was just some matrix, and I was just this was a matrix I made up out of nowhere. It's got nothing special, but it's just a matrix A. And then I picked this vector X for a reason, and you'll see in a second. But if I take this vector X and I take the dot product of it with this row and with this row, I get 0 and I get 0, okay? So in other words, this vector here is orthogonal to both of these rows. Okay, do you believe me on that?
Yeah.
Okay, so since it's orthogonal to both of these rows, then that means that this vector lives in the orthogonal complement of the row space, okay? It's orthogonal to both of the rows, therefore it's orthogonal to every linear combination you can build up using those rows. Is that okay?
Yeah.
Okay. So, well, let's see now what happens when we take this vector and we multiply by the matrix. Well, when you do that, when you take this matrix and multiply by the vector, the way that I think about matrix multiplication is that I take the first row and I take the dot product with with this thing. So I do like this row, dot product with this vector, and that gives me the number that goes right there.
Mhm.
But because my vector is orthogonal to the first row, I just get 0 in this spot. Then I want to figure out what goes in this spot. I take this row and I do the dot product with the vector. And again, because they're orthogonal, I'm going to get 0 here. So if a vector is orthogonal to both of the rows, that means when you multiply it by the matrix, you just get 0, 0. Or in other words, that tells you that the vector also lives inside the null space. So if a vector is orthogonal to the rows, that means when you multiply by the matrix, you just get 0, 0, which means it lives in the null space. And so that kind of shows you that things that live in the null space really, something lives in the null space if it's orthogonal to the rows and vice versa. If it's orthogonal to the rows, it lives in the null space.
Right. So
okay?
you're saying that if, well, because V1 is just, because it matches the first row in A, it's going to be orthogonal and you're going to get 0 out of that? Or like, where's the vector coming from? Because you just made up the vector in this case, -2, -3, 1, 0. But in the case of the example, there's not really one of those vectors. Sorry, was that convoluted? I can't hear.
Looks like you're muted.
That question was just too profound.
Speechless. You just left him speechless. Or even better, you took the words right out of his mouth.
Can you hear me now?
Yes,
we can.
Okay, so I don't know exactly what happens there. That has happened a few times. I don't know. The iPad just doesn't I don't know. It gives me some trouble sometimes. So, Tim, you were asking a question.
Yeah. So, I was just wondering, in the case of our example that we were just doing with matrix A,
yeah,
what the vector is that we're using, or we're not using a vector, I guess, but like
are you kind of wondering what the subspace is?
A little bit. Oh, but they give us the subspace already.
Yeah. So like in this case, there's no subspace really we're even thinking about. Like, I mean, we're talking about the row space and stuff, but there's not like a W that we're starting with. This is kind of like a fact that we're going to use in a problem about W, but the fact itself doesn't depend on a subspace W, if that kind of makes sense.
Okay. Yeah, we're good.
Yeah.
Thank you.
So no problem. So if we go back to this one, then the whole setup is we have our subspace that we care about. Okay. What we do is we build a matrix. We sort of custom build this matrix so that it has the row space that we care about. And now that it's written in terms of the row space of a matrix, we know how to find the orthogonal complement. And that's just finding the null space, okay? So whenever you're looking for a basis of an orthogonal complement, or if you're looking for vectors in the orthogonal complement, you can always take the vectors you already have, turn them into the rows of a matrix, and then find something in the null space of that matrix. And that comes in handy when you're doing like SVD examples, because remember, sometimes when you're building your U matrix, you don't have enough U vectors to build the U matrix. So what you try and do is you try and find a new U vector that's orthogonal to the ones you already have. And this is exactly how you do it. You put the U vectors you already have as the rows, and then you find something in the null space. And that guarantees that the vector you found is orthogonal to the rows. So I said a lot there. Have I lost anyone or?
That
No?
makes sense.
Okay. So let's go ahead and let's look at, let's take this matrix here. I'm just going to copy it. Let's find something in the null space. Or let's find a basis for the null space. Okay. So let's row reduce it down. Get rid of that green there. It's not needed. So let's row reduce. I mean, it actually is a row reduced, right?
Yes, sir.
So there's actually nothing really to do. We're just going to read off the first row tells us x plus y minus w equals 0. The second row tells us that z plus 4w equals 0. And then our free variables are going to be y and w are free. So let's solve for our leading variables. That tells me that x is equal to minus y plus w. Z is equal to negative 4w. And so if my vector is x, y, z, w, making these substitutions, okay. What I can do is I can split this up. This is the same thing we always do. I get negative 1, 1, 0, 0, plus w, 1, 0, negative 4, 1. Okay. Now I'm going to copy these because I want to go back over. So remember, what we've done here is we've found these two vectors here. These two vectors here are a basis for the null space of this matrix. Maybe I should write that down. Okay, they're a basis for the null space of the matrix, but remember the null space is the orthogonal complement of the thing that we want. So let's go back to our thing here. I'm just going to try and copy and paste these in, except I'm going to, remove the variables here. Okay, and that should be a basis for the orthogonal complement. Now, does anyone know how you could actually kind of verify that this is indeed a basis for the orthogonal complement?
You take the dot product between the vectors and the rows in A.
Yeah, exactly. So you could, or even if you wanted to go back to the original ones, you could take this vector, and you could take the dot product with the two vectors you started with. Okay. Now that should be they should be orthogonal, so you should get 0 in both cases. Also, you know that it's a basis because it looks like they're linearly independent from each other. Also, everything that we're talking about lives in R4. It looks like our subspace W, because these vectors are linearly independent, it looks like our subspace W is dimension what?
2.
Yeah. So because these vectors are linearly independent, it looks like our subspace W has dimension 2. And since we're in R4, what would you expect the dimension of the orthogonal complement to be?
2.
2, right? So we've got two linearly independent vectors that are orthogonal to V1 and V2. That kind of verifies for us that it is a correct answer there.
So
okay?
Geometrically, is it just two perpendicular planes for the space?
Yeah, and that's really hard to picture because in R3, if you draw two planes in R3, they have to sort of intersect along a line. There's just not enough dimensions in R3. But if you go one dimension higher, they would just be two perpendicular planes, just like two perpendicular lines would look in R2. It's kind of a trippy thing because they just intersect right at the origin. These two planes don't intersect anywhere else. It's really weird, but
oh shoot, They only intersect at one point?
Yeah. Yeah. And
Oh.
that's, yeah. So it's kind of like, you know, when you have extra dimensions, things intersect less and less. So for example, if I was inside of R2, right? You know, if I wanted to draw a plane inside of R2 and a line inside of R2, well, the only plane I can have inside of R2 is going to be all of R2, right? So that's my plane. If I wanted to draw a line inside of R2, then that line sort of has to intersect the plane in infinitely many different points, right? Because there's just not enough room to sort of have a line and a plane that don't intersect in infinitely many points, right? But if I move up one dimension to R3, now I can kind of tilt my line so that it points right through the plane. And in R3, I can get sort of a different picture where my plane looks like this and my line just sort of points right out of it. So it's kind of like, it's this weird thing where in lower dimensions, you don't have enough room for things to sort of, everything sort of has to intersect more. But when you get to higher dimensions, things can kind of intersect less. I don't know. Any other questions on this? I love, so the math that I studied, like my research it's called low dimensional topology, but a lot of it sort of centers around 4-dimensional manifolds. So I like to think about 4-dimensional things, and I'd talk to you all day if you got me started on 4-dimensional things. Did you know, okay, here's a fact, okay, that'll kind of trippy. So do you know how you can take like a piece of string and you could like, say you had a piece of like a necklace, right? And it attaches at both ends. You could sort of undo the necklace, you could tie it in a knot, and then you could do it up again, and there'd be like a knot in the necklace, right? In 4 dimensions, you could take a basketball, and if you could kind of like undo it, part of it, you could actually tie the basketball in a knot and kind of close it up again. And so like a basketball could be knotted inside 4 dimensions. Just like a necklace could be knotted inside 3 dimensions, okay? So yeah. Those are fun things to think about if you're prone to thinking about those sorts of things. All right, we will not test you about knotted basketballs on the exam though, so let's proceed on to things that will show up on the exam. So next question, let W be the subspace of R4 spanned by these 2 vectors, and let V1 and V2, and let Y be this vector. Let's find the projection of Y onto W and the perpendicular component of Y to W. This is a fairly straightforward computation. Does anyone want to see me do it? I mean, it's not super conceptual. You do? Okay. So remember, we have the formula. I wonder, here, can I try something here? I keep running out of room here, but I'm going to try something. If this is too hard for you to read, I know I can do this. I know I can do this. I saw this the other day, and it was really handy. I think I can do a split screen. Okay, so question: if I sort of have my scratch work on the right side and the test on the left side, can you all see that? Both of that, read that sort of clearly enough?
Yep.
Can anyone not see it, I guess, is the better question. Just I want to make sure no one is kind of left out of this. Okay. All right, this might be a bit of a better way to do it, just so I can kind of have enough room for scratch work, okay? So remember, so W is the space spanned by these vectors. So I've got 2, 1, 0, 1, and 0, negative 1, 1, 1, okay? And I want to find the projection of the vector y onto W. So this is going to be, the formula for this is just a formula we learned. So this is going to be v1 dot y over v1 dot v1 times v1 plus v2 dot y over v2 dot v2 times v2. Okay, so this is just kind of a formula you have to kind of have memorized, or you have to know it. Now the question is that there's one thing we need to check before we use this formula. Does anyone know what that one thing is?
You just have to make sure that the dot product of V1 with itself or V2 with itself isn't 0?
Do they have to be orthogonal?
Yeah. Oh, that's a good thing. So yeah, you have to make sure we're not going to be dividing by 0, and that's important here. If we check these, we see that neither of these are the 0 vectors, so we're in good shape here. What was the other comment there?
That they were orthogonal to each other.
Yeah. So these vectors have to be orthogonal to each other. If they're not orthogonal to each other, then we're in trouble. Okay. So they need to be an orthogonal basis. Okay. Are these two vectors here orthogonal?
Yeah.
You bet they are, right? So so if they're not orthogonal to each other, the formula doesn't work. Okay, you'll get the wrong answer. So if they weren't orthogonal to each other, what would you have to do?
Gram-Schmidt.
You would have to do Gram-Schmidt, right? Now, fortunately, we don't in this case, so we can just go ahead and use the formula. So y dot v1 is going to be 2 plus 2 plus 2. So I think that's 6 upstairs. Downstairs is v1 dot v1, so it's going to be 4 plus 1 is 5 plus 0 plus 1 is 6. So we get 6 over 6. That is a nice treat there because that'll cancel. And so we get times v1. And then plus v2 dot y is, let's see. So v2 dot y is negative 2 plus 1 plus 2. So negative 2 plus 1 plus 2 is negative 1, right? Correct me if I'm wrong. Negative 2. Yeah. So I think that's negative. No. That's negative 2 plus 1 plus 2 is just positive 1. Okay. Then downstairs is v1 dot v1, which is just 1 plus 1 plus 1 is 3. And then times v1, 0, negative 1, 1, 1. So if we add these up, we're going to get 2. Then we're going to get 1 minus a third is 2/3. We get 0 plus a third is 1/3. And then we get 1 plus a third is 4/3. I think that's correct. Is everyone okay with that? Application of that formula. Now so that's the projection component. So 2, 2/3, 1/3, and 4/3. And then what's the perpendicular component? How do we find that?
It'd be y minus the projection of y on the w, right?
Yeah, exactly. So we just take y and then we subtract off the projection piece. And this is, so y was 1, 2, 1, 2, minus the projection piece, 2, 2/3, 1/3, and 4/3. So negative 1, 6/3 minus 2/3 is 4/3. 3/3 minus 1/3 is 2/3. And 6/3 minus 4/3 is 2/3. Okay, if I've made a mistake with the algebra, let me know. What's a good check we can do in this example to sort of hopefully verify that we've done things correctly?
You add them both together, you should get y, right?
Yeah. So we can add them both together. We should get y. We also should notice that these two vectors should be orthogonal to each other, right? One of them lives in W, one of them lives in W perp, so they should be orthogonal. And if we check that dot product, we get, I'm just going to do this here. So we get negative 2 plus 8/3 plus 2/3 plus 8/3. That doesn't look right.
It's supposed to be ninths.
Ninths? Oh, ninths. Yeah. Yeah, of course. So that's like negative 18/9, and then we have 18/9 on the other side. So yeah, so this is 0. Perfect. Good. So you can almost be certain that this is correct because we've, I mean, again, there's a possibility you got it wrong and you made some really unlucky mistake where they ended up still being orthogonal. But if you check them and they're orthogonal, almost certainly you've got it right.
Wait,
Questions there?
So all three of those components should be orthogonal to each other, or just y and the projection of y onto w? If you were to rearrange the equation, which components would be orthogonal?
This equation here?
Yes.
Well, so the only two pieces that have to be orthogonal to each other are the projection piece and the perpendicular piece.
Okay.
So I guess, okay, so this thing here should be orthogonal to this thing here, okay? Also, the perpendicular piece should be orthogonal to the vectors v1 and v2 because those also live in W. So anything inside of W, like this vector, or this vector, should be orthogonal to this last piece here because it's in W perp. Okay. Everyone okay with that?
So Dr. Hughes, on the other practice test for last semester, the two vectors it gives you in the subspace W, they're not orthogonal to each other. So you have to first make, like you do Gram-Schmidt is what you're saying?
Yeah. So if these two vectors weren't orthogonal to each other, you would have to still find an orthogonal basis. So you would take the vectors you have and you do Gram-Schmidt, yeah. Which would be a pain, but I think the reason that you see this example on this test and you see the other on the practice test is because this one works out a little nicer and we wanted to give it to you on the test. So other questions?
Is it okay if you just go over what the process of Gram-Schmidt does? I remember kind of how to do it, but I'm a little unclear on what it's actually doing.
Yeah, so the idea behind Gram-Schmidt, you're okay with how to do it? Is that what you're saying? Just not what it's doing?
I'm okay following the formula. I'm just not super clear conceptually or geometrically what it's.
Okay, so here's kind of the formula. You start off with these x vectors here, and you say, okay, I'm going to take my first vector just to be the first x vector. I'm just going to leave the first vector the same. Then for my second vector, v2, what I'm going to do is I'm going to take the second vector in my list, and I'm going to subtract off this piece here, okay? So the question is what is this piece that we're subtracting off?
Well,
if we look at the picture here, suppose we start off with like a u vector and a w vector. I've got them labeled differently, but it's kind of the same thing. We have two vectors we're starting off with. We're going to keep the first vector the same, okay? And that's gonna make it into our list. That doesn't change. We just put that in our list. But for the second vector, what we want to do is we want to make sure that it's orthogonal to the first one. So what we do is we compute its projection onto the line spanned by the first vector, and that's this piece right here. And then what we do is we subtract that piece away from W, and when we do that, we end up with this piece right here, the perpendicular component, okay? And so essentially what we've done is we just keep this vector, this new vector, we subtract off the projection. That leaves us with the perpendicular component, and that perpendicular component is the vector that we hang on to, and we put it into our list. And then we do the same thing again with the next vector, v3. We take x3, and now what we're going to do is we're going to subtract off the projection onto the subspace spanned by the two vectors we have now, and we're just going to keep the perpendicular part. So at every stage of the game, you're taking the vector you're interested in, and you've already got some vectors you've already processed, and you take the vector you're interested in, and you replace it with the orthogonal component to the space spanned by the vectors you already have. Is that okay? I forget who asked that.
Yeah, I think that's okay. So it basically takes subspace and turns it into an orthogonal basis.
Yeah, you're taking a basis for a subspace and you're converting it into an orthogonal basis for that subspace.
Okay, cool.
Yeah, and at every step of the way, basically what you're doing is you're taking a vector and you're replacing it with the orthogonal component of that vector, and then you're working your way up.
Yeah, okay, cool, thank you.
Okay, cool. So the next one is state the precise definition of the following. The vectors v1 through vp span a subspace if every, say, vector x in W is a linear combination of v1 through vp. Okay. We probably won't give you any definition questions just because of the way that we are inputting our questions into the exam. So I wouldn't worry too much about definition questions here, but. Okay.
I can't
All right.
tell you what a relief that is.
Yeah. So but I mean, you kind of have to know the definitions either way, but we won't ask you just to say like, tell me what this definition is, because there's not a good way to sort of have you enter that.
Yeah, no, that's okay.
Okay, good. So here's a question. So if A is a 3x3 matrix and the determinant of A is equal to -3, what's the determinant of 2 times A going to be?
-24?
Yeah, so yeah, I think so, right? So remember, if we've got some matrix here, we've got some matrix A, B, C, D, E, F, G, H, I, right? If you multiply this matrix by 2, you're going to get something like 2A, 2B, 2C, 2D, 2G, and so on, right? And you can pull the 2 out of the determinant if you want, but you can only pull it out one row at a time, right? So I could pull the determinant, I could pull the 2 out of the first row, and that would give me a factor of 2 in front. I could pull the 2 out of the second row, that would give me another 2 factor. And then I could pull the determinant out of the 2 out of the third row, and that would give me another factor of 2. So overall, if I pull it out of each row, because it's a 3x3 matrix, I'm going to get 2 to the power of 3 on the outside, but that's just 8. And so really, if the determinant was -3 to begin with, and I pull the 2 out, I get -3 times 8 is -24. Okay. Any questions on that? No? Okay. Do you guys mind holding on for 1 second? I just need to check on one quick thing. You might have heard some screaming in the background. My wife had to take my son to an orthodontist appointment that happened to be at this exact time, and so the other kids are kind of fending for themselves. So I just want to just poke my head out the door and just make sure everything's okay.
I'm gonna vote 18 on this next one.
Okay, we're good. All right. So that sort of tests you on whether you understand sort of how determinants change with respect to multiplying by a scalar. The next question is actually kind of similar. I guess I have paper here. I don't need to constantly write on the exam. Okay. The next question is kind of similar. They're giving you a determinant, right? They're saying the determinant of this matrix is 6. And then what they're doing here is they're doing some row operations, and they're messing up the determinant a little bit, okay? So what I would do with a question like this is I would start off with the matrix you have, D, E, F, 3A, 3B, 3C, and G, H, I, okay? And what I'm going to try and do is I'm going to try and do row operations to convert this into this determinant, into this determinant here, which I know the determinant of. So just looking at this, what do I have to do to sort of make these look the same? Well, first of all, I have to factor out a 3. So remember, I can pull a 3 out of a determinant, and that doesn't change anything if I do it for one row only. Okay, so I pull the 3 out. And now it looks like I just have to swap one row, right? Swap row 1 and row 2. So if I swap row 1 and row 2, what happens to my determinant?
It becomes
negative.
Yeah, it becomes negative. Okay. And so now what I have is I have this piece here, right? And I know what the determinant of that piece is. I know that the determinant of this thing is 6. So my overall determinant is going to be, so this piece here is just 6. So my overall determinant is going to be negative 18. Is that okay? So the way that I would do these questions is I'd kind of start with the determinant I'm curious about, and if I can kind of convert it back to the original determinant, then I can plug the original determinant in. But I just have to keep track of my row operations. And then remember, row operations or column operations, both of them are completely valid. So you can do column operations as well. All right, everyone okay? Keep rolling then.
What else? So switching a row makes it negative, and you can pull a scalar out. But is there anything else that we need to know about how it changes the determinant?
No, because then adding a multiple of one row to another doesn't change it at all. So those are the only 3 row operations we really do. So once swapping rows changes by a sign. You can pull a scalar out or put a scalar in, or you can add a multiple of one row to another, and it doesn't change things. So.
And swapping columns changes the sign?
Yeah, swapping columns. So exactly the same way. If I add a multiple of one column to another one, it doesn't change it. If I swap 2 columns, it changes signs. Or I can pull a scalar out of a column. Same thing. If you're not comfortable doing column operations, remember, taking a transpose doesn't change the determinant. So if you really wanted to do a column operation, what you could do is you could take the transpose of the matrix, and now your columns are rows, do a row operation, and then take the transpose again, and it doesn't, and so you've basically done the column operation by just doing row operations and transposes. Other questions there? All right, so let's keep going then. Suppose A is a 3x3 invertible matrix that is upper triangular and whose entry A11 on the first row and first column is equal to -1. What is the entry in the first row and first column of A inverse? Why are we doing this question? I don't know. It's a 3x3 invertible matrix. It's upper triangular, so I know, let's just kind of write down what we know. This is kind of a hard one to parse. So it's an upper triangular matrix. The entry A11 in the first row and first column is equal to -1. So the upper triangular part tells me I have zeros below the diagonal. Then it tells me what goes in the first row and first column. And then I guess we don't know what goes anywhere else. It doesn't tell us anything else. Okay. But it wants to know what is the entry in the first row and first column of the inverse matrix. So if this is A and this is A inverse, it wants to know what goes right here. So this is the question mark spot. Well, actually, the way I've written it,
it'd be -1, right?
Yeah, it's not super clear just by the way I've written it why it has to be -1, but I'm going to swap the order of these two. And by swapping the order of these two, at least to me, this makes it a little bit more clear what that number has to be. So I don't know what's in this spot or this spot, right? But when I multiply these two matrices together, I want to get the identity matrix. Okay, so if I want to know what goes in this spot here, the way I do matrix multiplication is I take this row and I do the dot product with this column, and that's going to give me the entry that goes right there. Now, because I have zeros in the second and third spot of that vector, I don't really care what goes on here. It could be anything. But I do know that the number here, when I multiply it by -1, I want to get +1 back. So I think the number there should be -1.
Okay, question.
Yeah.
So A inverse times A is the identity matrix, but
yeah,
what about A times A inverse?
It's also the identity matrix, but for me, the way that I think about matrix multiplication, it was just a little harder for me to see that. Like you could have solved it the other way too.
Oh, okay. You just did that to visualize it. Okay.
Yeah, it's harder for me to. I think through matrix multiplication in one way, and so it's easier for me to kind of see why it works that way. Yeah.
Okay.
But I think you could have done it the other way just as fine. All right, by doing kind of like a row column thing.
Can we also, can we take a minute and go over the invertible matrix theorem?
Yeah. Yeah. So the invertible matrix theorem is quite a theorem. You can do 3. No, I can't do 3. That was getting greedy of me trying to have 3 windows. Not that I was really wanting to do 3 windows, but let me see. Close that. Yeah, so the invertible matrix theorem, it actually shows up a few times in class. It kind of rears its head for the first time, I think, in chapter 3 here. where we first sort of see a bunch of things, and essentially what the invertible matrix theorem is doing is it's saying for a square matrix, a bunch of things are equivalent to each other, and they're all equivalent to the matrix being invertible. So for example, for like a 2x3 matrix, okay, oops, for a 2x3 matrix, you know, it's possible for you to have the columns spanning all of R2. It's, you know, like for a matrix that's not square, maybe the columns are linearly independent, maybe the columns span Rn, maybe, you know, like there's a few different things that can happen, but they're sort of not really all related to each other. However, for a square matrix, if the square matrix if the columns of a square matrix are linearly independent, then that means you have to have a pivot in every column. And because it's square, it means you have to have a pivot in every row as well, which means the columns have to span Rn, which means I don't know. Yeah, I don't know maybe how much time I don't know how deep you want me to go on this, but essentially for a square matrix to be invertible, that means that when you row reduce it down, you get the identity matrix, okay? Now, if you get the identity matrix when you row reduce your matrix down, that means that you have a pivot in every row and a pivot in every column, right? And so in general, having a pivot in every row tells you a bunch of things. Having a pivot in every column tells you a bunch of things, but they don't really tell you anything about each other, right? Just having a pivot in every row doesn't tell you you have a pivot in every column for a non-square matrix. But for a square matrix, having a pivot in every row implies you have a pivot in every column. So everything that goes along with having a pivot in every row, also you get everything that goes along with everything that goes along with having a pivot in every column. And so by the fact that your matrix is square, you get a lot of facts sort of all being equivalent to each other. I don't think I said that in a really good way, but essentially if you look through this list of items here, you're going to see that everything on this list can kind of be boiled down to the fact that you have a pivot in every row or you have a pivot in every column. And because we're assuming that the matrix is square, those two things are the same. Having a pivot in every row tells you you have a pivot in every column and vice versa. So kind of you've got this one group of facts that tells you have a pivot in every row, another group of facts that sort of tells you have a pivot in every column. And when your matrix is square, all those facts are sort of equivalent to each other. I don't think I sort of said that in a very good way, but whoever asked that question, are you sufficiently, is your question answered, or are you just sufficiently confused that you want to move on? Or do you want to talk more?
I'll say a little of both.
Okay, a little of both.
But we can move on.
No, I'm not saying we need to move on. I mean, this is definitely a good thing to understand. So let's maybe go through. Let me maybe pick out. Two of these things, or two or three of these things to kind of jump between. Okay. Let's see.
Is it okay if we talk about how the invertible matrix A times some vector X equals some vector B, how that has to have at least one solution?
Yeah. So so let's so the question you're asking is why does, you know, if AX equals B always has one solution, why does that tell you the matrix is invertible? Is that what you're asking?
Yeah, exactly.
Okay, so that if you think about it here for a second, okay, if you take your matrix and you set up an augmented matrix here, so say this is like, you know, this is just your A, you're writing it down as an augmented matrix. So when you row reduce this matrix, so essentially this thing here tells you that you have to have a pivot in every row, okay? Because if you don't have a pivot in every row, say you have something like this, okay? If you don't have a pivot in every row, then you really have to get lucky with your choice of B in order to get a solution, right? Because, for example, if you have something like this, 2, 1, 0, is this augmented matrix going to give you a solution? Anyone can answer. Does this augmented matrix have a solution?
Has an infinite number of
Yes.
solutions, right?
Yeah,
infinite.
it has infinite number of solutions, right? But the only reason it has solutions is because we got really lucky, and in that bottom spot we got a 0. You know, if you were to just sort of randomly choose a vector b and plug it in, well, chances are you're not going to get 0 in this spot. Okay, and so that means chances are the thing that you end up with is not going to have a solution because you have a bad row here. Okay, so if you don't have a pivot in every row, that means that for most of the time, you're not going to get a solution. Okay, and you really just have to get kind of lucky to get a solution. So if you don't have a pivot in every row, then you will not always have a solution here. So this statement would be wrong. Okay, so therefore, if you know that you always get a solution, what that tells you is that you really have to have a pivot in every single row. Okay, because if you don't have a pivot in every row, you're not always going to get a solution. So always getting at least one solution means you have to have a pivot in every row. Okay, but if you have a pivot in every row, okay, well, the only way I can have a pivot in every row if my matrix is square is if I also have a pivot in every column. So therefore, if I know that this part here is true, I know I have a pivot in every row. And if my matrix is square, that tells me I also have to have a pivot in every column, which means that when I row reduce my matrix, it looks like the identity matrix. Okay, and that's if your reduced row echelon form is the identity matrix, then you know that you're invertible. But again, like this fact, if you have a pivot in every row, right? So for example, if I look at this list over here, so part F, right? This thing here tells me I have a pivot in every row. Since I have n rows, that means I have n pivots. But that also tells me I have a pivot in every column. And if I have a pivot in every column, that means my columns are linearly independent, right? And if my columns are linearly independent, that means I have no free variables, which tells me this thing has only the trivial solution. So you can kind of see that basically all of these things are equivalent to each other, but the linchpin comes down to the fact that because your matrix is square, if you have a pivot in every row, it tells you also have a pivot in every column. And so you can kind of jump between any of these facts just based on that knowledge that you have a pivot in every row and every column. Is that kind of okay, Joshua?
Yeah, that's pretty good. That makes a little bit more sense.
Okay. So really, I would say the invertible matrix, like later on, the invertible matrix theorem includes things about eigenvalues and eigenvectors and singular vectors and things like singular values and stuff like that. But sort of for the first part anyways, it really all comes down to knowing where the pivots are. So
Dr.
keep that in mind. Yeah.
Why does it say there's at least one solution instead of just exactly one solution?
Well, because just saying there's at least one solution is just a little bit weaker. So it's like, you know, it's just a bit. You could say exactly what you said. There's exactly one solution, but you don't even have to know there's exactly one solution. If you know there's at least one solution and your matrix is square, then that's enough, right? So it's kind of it's a lower threshold, and so we put the lower threshold in there. But you could say your higher threshold as well. Kind of turns out they're the same.
Is there even a counterexample to say you can't? Is there a matrix that is invertible that has more than one solution to?
No, but the point is that if you're a detective, right, and you're trying to figure something out, you want to be able to figure it out with as few clues as possible, right? And so if I tell you there's at least one solution, that's kind of like a little bit of a clue, but it turns out it's actually telling you quite a bit. It's also telling you that there is exactly one solution. It's also telling you it's invertible, you know. So you could put what you said in there as one of these as well. But it turns out that logically, if you know one of them, you know all of them. And so we just happen to put kind of the weakest one in there.
Okay.
Is that okay?
Yeah.
Maybe the detective analogy wasn't helpful, but all right. So is that okay on our detour to the invertible matrix theorem, Joshua?
Yeah, I'm cool. Thanks for taking time for that.
Oh, no problem. I mean, this is a review, right? So that's the point, is to go and we can take detours and talk about anything you guys want. Just let me know. So the next two things are precise definitions. Those are things you can look up. They're also things that are not going to really show up on this exam. So unless you want to talk specifically about the definition of a linear transformation or the definition of an eigenvalue? Does anyone want to kind of talk about those things right now? I'm not going to write them down because we can kind of look them up pretty easily if we want, but.
Do you want to go over the linear transformation real quick?
Yeah. So remember, for our purposes, you know, a transformation is just a function, okay? And it's sort of, you know, it takes a vector, maybe our vector is in R2, and it spits out a vector, say y, which is, you know, maybe in R4, something like that, okay? So a transformation is just a function. I can plug in vectors of one dimension, and it spits out other vectors. Maybe those vectors are the same dimension, maybe they're dimension higher, dimension lower. We really don't know. But we always sort of denote, you know, if like in this situation here, our function takes in vectors in R2 and spits out vectors in R4, we would sort of denote that fact by saying that T takes R2 and maps it to R4. That's kind of the shorthand notation, okay? Now, transformations can be really ugly. Like you could put a sign in there. You know, your transformation might be something like, you know, T of xy is, you know, sine of x, you know, cosine y times tan of x. You know, it could be something really ugly, and we don't consider any of those really ugly things in this class. The only things that we really consider in this class are what are called linear transformations. And so a linear transformation is a transformation that satisfies two sort of key properties, okay? The first property is that when I take a vector x and a vector y and I add them together and then plug them into the transformation, that should be the same thing as plugging in the vector x and plugging in the vector y separately, okay? And then adding the result together. And then the same thing, if I plug in a vector c times x, where c is a scalar, that should be the same thing as just plugging in the vector x and then multiplying by c, okay? So linear transformations are special forms of transformations that satisfy these two properties. The nice thing about linear transformations is that if I define you some linear transformation using some formula or whatever, there's always going to be a matrix A that gives you that linear transformation, okay? So even if your linear transformation was like, you know, T of x, you know, I mean, we could give you a linear transformation or describe a linear transformation in a lot of different ways, but no matter how we describe it, if it truly is linear and it truly does satisfy these two conditions, then that means that there is some matrix A that gives precisely that transformation, okay? And so instead of thinking of it as being like plugging it into a function, you can think of it as the transformation as just taking a vector and multiplying by a matrix, okay? So are everyone okay on that, kind of?
Yeah, that's great, thank you.
Okay, now the one thing I want to add though is to find this matrix. This is called the standard matrix. Okay, and usually we denote it by sort of just drawing square brackets around T. So that's kind of the standard matrix. That's the matrix that describes the transformation. And the way that you find the standard matrix, remember, is you take the unit basis vectors, the standard basis vectors. So for example, if we were in R3, say our transformation was like R3 to say R2, I would take the standard basis vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, and I would plug each of those basis vectors into my transformation, and that would give me three vectors inside of R2, and those three vectors I get, those would be the columns of my matrix, okay? So if we ever give you the transformation and we ask for the standard matrix, all you have to do is take these special vectors, plug them into the transformation, and then those become the columns of your matrix, okay? Questions there?
And then if it's like a multi-step transformation that they described, then you just do that for each step and then multiply them together, correct?
Yeah. And the one thing in that case, when you're multiplying them together, the one thing you have to keep in mind is if you want sort of the transformation S to happen first and the transformation T to happen second, then what you have to do is you have to remember that you want to, when you multiply the matrices together, you want S to show up on the right, because when I multiply by a vector, the matrix that shows up on the right is the one that's the transformation that the vector x is going to see first. Okay, so if I were to multiply these out, x would see the s transformation first, and then once it's kind of done being transformed by s, then it would finally see the t transformation. So you just kind of have to remember that you kind of want to write them in reverse order from the way you want them to happen. Is that okay?
Yep, awesome.
Okay. So burning through digital paper here like there's no tomorrow. But I guess it's still the environmentally responsible way to do it. So
hey, you gotta save those Minecraft trees though.
Exactly. There are real humble Minecraft Minecraft loggers out there who are chopping down Minecraft trees, making this for us. So I never thought of it as Minecraft paper. My kids are going to get a kick out of that. Thank you. All right. So question D. If A is a 3x3 matrix with eigenvalues 1, 0, and -1, and then they give us the corresponding eigenvectors, and if X is equal to this linear combination of these vectors, then what is A to the 1001 times X? Okay. So here's a question. Could you tell me what the matrix A is? Have they given us enough information to build the matrix A? This is kind of a bonus question.
Yes?
Yeah, why, Matt?
Because we're given all of the eigenvalues and the corresponding eigenvectors.
Yeah.
And so we should be able to produce the original matrix.
Yeah, exactly. I mean, if you wanted to, you could actually write down what this is, right? They've given us enough information to build our P matrix. They've also told us the eigenvalues, so we could build our D matrix. So you really could sort of just go about, building the matrix P. If you wanted to know what A was, you could. But in this case, we don't actually need to know what A is, because if we want to, this is taking some like ridiculously high power of A and multiplying it by a vector. Obviously, you're not going to sit down and multiply A times A times A times A 1,001 times. There's got to be some shortcut here. And the shortcut is the following, okay? So when we take A to the 1001 and multiply by the vector X, well, remember, the vector X is equal to -2 times U minus V plus 3 times W. Okay, so if I multiply that matrix in, I get -2 times A to the 1001 times U minus A to the 1001 times V, and then plus 3 times A to the 1001 times W. Okay? Everyone good on that so far? So why does this help us? Well, remember, U, V, and W are eigenvectors with eigenvalue 1, 0, -1. Okay? So if we think of, like, for example, A to the 1001 times U, that's the same thing as just taking the matrix A and multiplying it by U 1001 times. Okay? But because U is an eigenvector, every time I multiply by A, what do I get?
Lambda times U.
Yeah, every time I multiply by A, I just get lambda times U, right? And since in this case, lambda is just equal to 1, every time I multiply by A, I'm really just multiplying by 1 every single time, okay? And so I get, that's the same thing as lambda to the 1001 times U, which is just 1 to the 1001 times U, okay? Same thing over here. Every time we multiply V by A, what do we get? We just get 0 times V, right? And the first time that happens, it just kills everything, right? So it gives us 0 to the 1001 times V. And then finally, the last thing is we get -1 to the 1001 times W, okay? But these are all actually pretty simple to figure out now. So the first thing just gives us -2 times U. The second term is gone completely. And then the third term is just 3 times well, -1 to the 1001 is -1. So we get -3 times W. Okay. And if I actually plug in what these vectors are, was there a question there?
Yeah, Professor Hughes, could you repeat why you can replace A with the eigenvalues again? I missed that, sorry.
Oh, sure. So let's do something more reasonable. A to the power of 3 times, let's do the W vector they gave us, okay? So let's do A to the power of 3. Well, this is just the same thing as A times A times A times W, okay? Now, remember, W is an eigenvector. So A times W is just equal to lambda times W. And in this case, lambda is just equal to -1. So A times W is equal to -1 times W. Is that okay? I didn't see who asked that. But
yeah, that's perfect. I forgot about this equation that you just wrote down up there.
Okay, yeah. And then so then like every time you multiply by A, you get a -1, right? And you can pull that -1 out, multiply by A again, you get another -1. So the point of this question is not to obviously have you build a matrix and take a really, really high power. It's to see, can you kind of do some eigenvalue algebra? And
Right.
yeah. And so in this case, we sort of the matrix kind of disappears. And we just get these scalars, but these scalars are kind of easy to deal with. And so in the end, you get -2, -3. So I think this is -5. -2, -6 is -11. And then -2. So I think this is our answer.
Cool. Thank you so much.
Yeah, no problem. -5, -11, -2.
Okay,
Questions?
for you.
Yeah.
So would we do the same setup if we were just trying to find like A to the 60th power and we were given like the matrix A? Would we find the eigenvalues and find the eigenvectors and everything, and then just multiply the eigenvalues by that power if we didn't have this X function or formula rather?
Yeah, so what happens in that case, yeah, I think I maybe I didn't quite follow what you were saying, but in that case, if you if A is equal to P times D times P inverse, is this what you were talking about? And like A to the power of 60?
Yeah.
So when you want to raise A to the power of 60, you kind of do the same thing, but it turns out that you have P D P inverse times P D P inverse, all the way up to P D P inverse, and all these sort of P inverses and P's in the middle disappear. So the only thing you're left with in the end is P times D to the power of 60 times P inverse. And so I think what you were asking, you can correct me if I'm wrong, is in that case what you would do is your D matrix, instead of just being like lambda1, lambda2, lambda3, it would be lambda1 to the power of 60, lambda2 to the power of 60, and lambda3 to the power of 60. Was it you, Maddie, that asked that?
Yeah, perfect. Thank you.
Is that what you were asking?
Mm-hmm. And then we would
Okay.
so then the answer of A to the 60 would just be equal to D to the power, P times D to the power of 60 times P inverse.
Yeah, you'd have to multiply the P and the P inverse at the end. Yeah.
Awesome. Thank you so much.
Yeah, no problem. All right. So again, I can't see, maybe I should check chat. I haven't seen if there's been any chat going on, but if you do have a question, again, just feel free to chime in, and even if I'm in the middle of a sentence, we can
That should be
talk.
-5, -11, and -2, shouldn't it? Because you have -2, -6, -8.
Wait, what should it be?
So it should be -5, -8, and -2.
Oh, -2 minus 6 is -11.
Isn't that -8? Too much.
Oh yeah. Yeah.
Yeah, just low-key. Just wanted to make sure I hadn't gone crazy. I was like, oh no.
Yeah. Why did I think I had a 5 in my head. So I had like -2 times, I think because I was like multiplying -2 and 3, and then I think in my head I was also adding them, and then I was adding everything together. That'll be my excuse. I think that's what happened. Okay.
Let's go with
perfect.
that. We'll go with that.
Do we know how to solve a problem like this if the eigenvalues are not 1, 0, and -1?
No, I mean, yeah, like we'd have to give you I mean, we're not going to ask you to raise like 2 to the power of, you know, to the power of 1001. Like we give you numbers that it works out nicely. Yeah. I mean, the algebra would still work out, but we just wouldn't want to be like taking such high multiplying such high powers and stuff together would be tricky. So, questions there? All right. Let's see. So, do you guys mind if I just go fill up my water bottle here? Just grab a drink real quick. I'll be like 2 seconds. All right. Okay. So let's see. So the next question is a spectral decomposition. Then let's do the spectral decomposition one, just because it'll give us some practice with eigenvalues, eigenvectors again. Then would you all want to jump to some more multiple choice questions from the practice exam from last semester? Just more conceptual ones? Sure. Okay. 1 thumbs up. That'll count. So let's do this E one, and then instead of going on to the long answer, I know I think I said I'd do long answer. I forget what I said about that, but instead of doing long answer, which are typically just more computational, we'll jump over to some more conceptual ones again. Because in general, I think most students have said they struggle with the conceptual ones. So let's write down the spectral decomposition of this matrix. So remember that the spectral decomposition is where you take a matrix and you find unit eigenvalues, you find unit eigenvectors, I should say, and then you build up this thing here. So it's kind of like the outer product form of the singular value decomposition. The difference is the outer product form of a singular value decomposition works for any matrix at all. Absolutely any matrix, doesn't have to be square. The spectral decomposition only works if your matrix is symmetric. Okay, so that's really the difference between the two. Is one of them only works if your matrix is symmetric. The singular value decomposition works anytime. So let's go ahead and let's do the spectral spectral decomposition here. Okay. So so the first thing is we want to find eigenvalues and eigenvectors. So to find the eigenvalues, we're going to find our characteristic polynomial. And I guess we should check to make sure our matrix is symmetric, otherwise this won't work. Okay, so the determinant of this is going to be 2 minus lambda squared minus 9, lambda squared minus 4 lambda minus 5, and I think this is going to factor nicely as lambda minus 5, lambda plus 1. Okay. So our eigenvalues are going to be lambda 1 equals 5, and lambda 2 equals -1. Is it a problem that we got a negative eigenvalue here? Should eigenvalues of matrices not be negative?
I think only in the singular value decomposition are they non-negative, right? Because you take A times the transpose of A, or A transpose times A.
Yeah, exactly. If you're looking at a matrix A transpose A, then you should never get negative eigenvalues. But this matrix wasn't of that form. This is just some symmetric matrix. So finding negative eigenvalues is fine. So now we just want to find the eigenvectors. So we'll start off with, say, lambda 1. So A minus 5 times the identity is -3, 3, 3, -3. This row reduces nicely to 1, -1, 0, 0. And so therefore x is equal to y is free. So my vector x, y becomes yy. Okay, and so my so 1, 1 is an eigenvector. Okay, now because I'm trying to do spectral decomposition, or if I was trying to do if I was trying to orthogonally diagonalize, I want to make sure this vector is a unit vector. So I'm going to take u1 to be 1 over rad 2, 1 over rad 2. Okay. Again, I want it to be a unit vector. So whenever we're doing spectral decomposition, singular value decomposition, or orthogonal diagonalization, we always want to make sure that our eigenvectors are unit vectors. Then let's do x2 is equal to -1. So a plus 1 times the identity is 3, 3, 3, 3. And when we row reduce this down, we get 1, 1, 0, 0. And therefore, x is equal to -y, y is free. And my vector xy becomes and so my second eigenvector, again, I'm going to normalize, becomes -1 over rad 2 and 1 over rad 2. Okay. So if I wanted to orthogonally diagonalize, I could, right? I mean, I've basically got all the information. I would write down my Q matrix would be 1 over rad 2, 1 over rad 2, -1 over rad 2, 1 over rad 2. That'd be my Q matrix, and my D matrix would be 5, -1, 0, 0. Okay. So I could do that, but I'm actually trying to do a spectral decomposition. So that's not what I'm looking for, but I just thought I'd add that in there. So for the spectral decomposition, remember the thing that we want to do is we want to sort of build this formula here. So I'm going to plug in my eigenvalues and my eigenvectors, and I'm gonna go from there. So the spectral decomposition tells me that A is equal to lambda1, which is 5, times u1, 1 over rad 2, 1 over rad 2, times u1 transpose. Okay, plus, through the magic of television, plus this piece here, but instead of a 5, we get a -1. So it'll be a -1 times this thing here. And then we get a negative signs.
Oh yeah, negative signs.
There we go. Yeah, so the negative sign shows up there. Okay, so we've just plugged into our formula. Let's multiply these out to see what they look like. So we get 5 times 1 over rad 2 is 1/2. 1 over rad 2 is 1/2. 1/2 and 1/2 minus -1 over rad 2 times -1 over rad 2 is 1/2 minus 1/2 minus 1/2 and 1/2. Okay, so you can kind of see that both of these matrices are pretty simple. I mean, the matrix we started out with was really simple, but yeah.
Professor Hughes?
Yep.
I know there was a reason for doing spectral decomposition. It was something to like make hard matrices more simple, but could you remind us of that, or at least me?
Yeah, so the idea is in this case, it's not quite so evident why we would want to do a spectral decomposition or a singular value decomposition. But typically speaking, you could have a big matrix, and it could be a bunch of data that you've collected over. If you're an advertising executive, or maybe you're a physicist who's done a bunch of experiments, you have some big matrix of data, and that matrix will generally have like very, very high rank. Okay. So the idea behind the singular value decomposition is that a lot of that data might be sort of noise, and it might not be really important to your data set. So what the goal is you want to take your big data set and you want to reduce the rank of it, okay? You want to basically break it up into simpler pieces that you can then kind of study and understand better. So somehow by looking at like the spectral decomposition of our matrix here, because the eigenvalue here is 5 and the eigenvalue here was only -1, somehow this matrix is sort of contributing more to the matrix A than this matrix is, okay? And so because one of them is sort of contributing with a factor of 5, and one of them is sort of only contributing to a factor of 1, you know, if you wanted to reduce the rank in sort of a sensible way, you would probably just take the piece that's only contributing to a factor of -1, and you would throw that away, and you could kind of convince yourself that the piece that you've kept behind, in other words, this piece here, is closer to the original matrix than sort of any other decomposition would be. So it's kind of a way of taking a complicated matrix, complicated data set, compressing it, making it sort of simpler while still retaining most of the important information.
Okay, perfect. Yeah,
cool.
That makes sense.
So when we input our answers for this, do we want to multiply out the matrices for each?
It doesn't. You mean like multiply the 5 in?
What I mean is like multiply U1 by U1 transpose.
Yeah, I think probably multiply U1 by U1 transpose. It doesn't so much matter if you multiply the 5 or the 1 in. I think like an answer like this would be suitable.
Okay.
If a problem like this comes up, we'll tell you how to do it. So
Same
we'll tell
thing
you
with
exactly what we want.
SVD.
Yeah.
Okay.
Yeah.
Cool.
All right. So we're actually more or less out of time. I'm kind of okay to go on. There was actually one person I was supposed to talk to after this. So I just want to check with that person real quick just to make sure. If we're okay kind of going longer, then I'm fine going longer, but let me just check one thing here real quick. Certainly you're welcome to go anytime if you want, but I talked to kind of someone. Oh yeah. Yeah, okay. Let me just ask a question here in the chat. Oh, okay, he messaged me. I was just about to, yeah. Okay, so we'll kind of go on a little bit longer here. I just had an appointment with someone else. I wanted to kind of make sure I wasn't. Okay. 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 So I had like a really kind of, it wasn't like super embarrassing, but I didn't really know how the chat feature worked in Zoom. So I was in a seminar with probably 40 people, and someone asked me a question privately, and I thought if I just went in the chat window and responded, it would just be another private message like most other things, but it definitely wasn't a private message. And I was kind of making a joke about, and it was a joke that it was just a joke that, anyways, I would have to explain way too much context, but yeah, never mind. Anyways, okay, so yeah, so let's go on for at least a few more minutes here, and yeah, just a reminder, I will have sort of virtual office hours on Friday, Monday, and Tuesday of this week. I forget exactly what hours I said, but they're in that email I sent out yesterday, and I think they're also on Learning Suite. So so let's do the practice final from last semester, and we'll just try and zip through as many of the multiple choice questions here as we can. Again, I think people have the most trouble with these ones, so we'll try and do as many as we can. And again, stop me if you have questions. So suppose that A is a 3x4 matrix with a pivot in each row. Which of the following must be true? Mark all that apply. So whenever I see a question like this, I always just kind of like to write down, I just like to have a visual in my mind. So it's a 3x4 matrix. I'm told that it has a pivot in each row. So, you know, maybe it's something like this, and then who knows what else happens. I mean, it doesn't have to look exactly like this. The important thing is that I have a pivot in each row, okay? And I sort of keep track of that fact. Mark all that apply. So the first one is the equation AX equals B has infinitely many solutions for every B in R3. Is that going to be true? Will it always have infinitely many solutions no matter what B vector you plug in?
Yes, sir.
It will, right? And the reason is because if we sort of, you know, if we sort of write this down as an augmented matrix, because I have a pivot in this spot right here, I have a pivot in every single row, I'm never going to get one of these bad rows, right? So there's always going to be at least one solution because I never get a bad row. And then also, because I don't have a pivot in every column, I have to have a free variable. And therefore, not only do I get at least one solution, I'm going to get infinitely many. Okay. The columns of A are linearly independent. Is that possibly true? It's not, right? In order for the columns of A to be linearly independent, it would have to have a pivot in every row, right? In this case, or sorry, pivot in every column. In this case, we definitely don't. The equation AX equals 0 has a unique solution. Yeah, thumbs down, right? This is, again, the same thing as the previous one. We don't have a pivot in every column, therefore we have free variables. Therefore, we're going to get infinitely many solutions, okay? There is a B vector in R3 for which AX equals B has no solution. Again, because we have a pivot in every row, we know we're never going to get a bad row no matter what B vector we plug in. So therefore, that's also false. The nullity of A is equal to 1. What is the nullity of a matrix? Can someone tell me the definition of the nullity?
Isn't it, it's the number of free variables. It's also like the space where AX is going to be equal to 0.
Yeah. So it's the definition is it's the dimension of the null space, right? Right. It's the dimension of the space of all vectors that when you multiply by A, you get 0. Okay. So the definition says it's the dimension of the null space, but ultimately the dimension of the null space, when you look for a basis for the null space, the number of vectors you get in that basis is always the number of free variables you have. So the dimension of the null space is always the number of free variables. In this case, we have exactly one free variable, and therefore the nullity is equal to 1. Okay. So the nullity is the dimension of the null space, but again, it's just the number of free variables. So you can kind of think of it in those two different ways. The columns of A span R3. What do you have to check for in order to see if the columns of A span R3?
Linear independence.
Yeah. Sorry.
But from at least 3 of those, right?
Yeah. So in order for the columns, yeah. So I see what you're saying. Yeah. So really, if we have a pivot in every row, I mean, yeah, if you have a pivot in every row, that means you have 3 pivots, and that means that 3 of the columns are linearly independent. And since you have 3 linearly independent vectors in R3, they have to span R3. So that's one way to look at it. The other way is just anytime you have a pivot in every row, you know that the rows are going to span Rm. So, and then the last one, the rank of A is equal to 4, is how do you tell the rank of a matrix?
number of pivots in the rows?
Yeah, it's the number of pivots. The rank is always the number of pivots. And in this case, we have 3, so that's not equal to 4. Good. Any questions there? Feel free to stop me if you do. Okay. Moving on then. I can't see. Like somehow, never mind. I'll get Zoom down. I think I will master Zoom. My mastery of Zoom will be sort of proportion or sort of related to how close we are to developing a vaccine to coronavirus. And I think the day that the vaccine gets related, I'll sort of have mastered the last sort of features of Zoom that I need. All right, so suppose that U is an n by n orthogonal matrix. Which of the following must be true? So this is going to be about a bunch of properties of orthogonal matrices. The first is U has distinct eigenvalues. Does that have to be true? Can you come up with an orthogonal matrix that has the same eigenvalues, repeated eigenvalues? Well, I can. Here's my favorite orthogonal matrix, the identity matrix, okay? The identity matrix has eigenvalues 1, 1, and 1, and they're definitely not distinct, but it is still an orthogonal matrix. The inverse is equal to the transpose, so it has orthonormal columns. So orthogonal matrices definitely don't have distinct eigenvalues. The columns of U are linearly independent. Is that true or not? It is true, right?
I support that statement.
Good. Okay, so Matt's on board. So remember, the columns of an orthogonal matrix are orthonormal. And remember, orthonormal vectors are always linearly independent. So the columns are definitely going to be linearly independent. Another way to look at it is, remember, an orthogonal matrix is always invertible, and invertible matrices always have independent columns. Every eigenvector of U has length equal to 1. Is every eigenvector of U going to be a unit vector? It's kind of a trick question, because remember, when we're like doing orthogonal diagonalization, remember we make sure everything is a unit vector. But remember, if I have a vector x, suppose it's an eigenvector, right? Well, remember, any scalar multiple, so anything like 2 times x or 3 times x, these are also, 174 times x. These are also eigenvectors. Okay? And they're eigenvectors for the same eigenvalue. So whenever you have an eigenvector, you can always scale it by any constant you want as long as it's not 0, and you're going to end up with another eigenvector. So certainly, maybe you start off with an eigenvector of length 1, but you could always double its length and it would still be an eigenvector. So this one's definitely false. Okay. Everyone okay on that? All right, the rank of the matrix A is equal to n. Well, if our matrix is invertible, remember any invertible matrix has to have full rank, okay? So if our matrix is 3 by 3 and it's invertible, we know the rank is equal to 3. And that's because, it's going to have a pivot in every row and a pivot in every column. So therefore, if our matrix is n by n, we know it's invertible. We know it has to have a pivot in every row and every column. Therefore, the rank is n. The next one, the determinant of U is equal to 1. Does that have to be true?
Couldn't it also be -1?
Yeah, it could also be -1. So that's a trick question. It's almost true, but it's not quite true. U transpose times U is the identity matrix. Yeah, that's kind of one of the key facts that we know about invertible matrices. The transpose is the inverse. What about this next fact here? The dot product of Ux and Uy is equal to x times y, x dot y.
Well, U won't change the magnitude of x or y, and it shouldn't change the relationship between them, right? So
yeah, so that's kind of that theorem that we talked about a little bit earlier today, is that orthogonal matrices don't alter the dot product of vectors. And so if you start off with a vector x and y and you multiply them by a matrix, the dot product is going to stay the same. And geometrically, we think of that as sort of preserving angles and lengths, but really what's happening is it just doesn't change the dot product, and that's kind of why it happens. And then the last one, U has orthonormal columns, and that's certainly something that we know about orthogonal matrices. That's kind of part of the definition. So, all right, any questions on that one?
Yeah, I got one really quick.
Yeah, go ahead, Tim.
So I'm just fact checking myself, but if a matrix is orthogonal, does that mean it is always invertible too? Like, do they just go hand in hand?
Yeah.
Okay.
Yeah, I mean, obviously not every invertible matrix is orthogonal, but every orthogonal matrix is invertible. So orthogonal really means two things. It means it's n by n, so it's a square matrix, and it has orthonormal columns.
Right.
And if those two things are true, then it means that your matrix is invertible, and it means that the inverse is just equal to the transpose. So.
Okay.
Yep.
Gotcha. Thank you.
Yep. Okay.
And just to clarify,
yep.
Orthonormal columns means if we multiply one column by the other, we get 0?
Yeah, and then if you multiply any column by itself, or do the dot product, you should say, you get 1.
Okay.
Yeah. Okay, so 3 and 4 are computational ones. Find the singular values and perform the Gram-Schmidt procedure. Let's see.
We talked a little bit in class about when we're doing the Gram-Schmidt process, we can simplify the vectors and then normalize them at the end.
Yeah.
I think I've tried to do that, but I think on the homework I kept getting the wrong answer. Do you have to keep track of like the coefficients and stuff that you use to simplify the vector, or?
Okay, so getting the wrong answer, that might have unfortunately been just a feature of Learning Suite. It might not have been robust enough to check whether the answer you got is correct. On the exam, you don't really have to keep track of the coefficients. So if you get a really ugly V2 vector in Gram-Schmidt and you want to go ahead and find V3, you can scale V2 to be whatever you want to make it look a bit nicer. And there's no sort of compensation you have to keep in mind. It should still work. WebAssign might have just been looking for sort of one specific answer, and they didn't. And so unfortunately, that's the problem with WebAssign, is that they're not, some questions are really good at like checking different ways you can do it, and some aren't as good. On the exam, if we give you a Gram-Schmidt question, we'll check for all possible correct answers. We won't just check for one specific one. So on the exam, you can do either, but just, yeah.
Okay.
Hopefully on the exam, the numbers will work out nice enough that you won't really need to concern yourself with that. So, okay. So I have about 10 minutes left here. Maybe instead of sort of getting neck deep in a computational problem, typically those end up being a little bit more straightforward. It would be more prudent for us to kind of do, a few more conceptual ones if people are okay with that. Somehow I've like shrunk my window too big. This is really kind of causing some issues here. Okay, I don't know what I've done, but I made my window too big, so I can't see yeah. So let's maybe skip these purely computational ones. I mean, for the singular value decomposition, what we would do is, remember, if we want the singular values of a matrix, we would take A transpose A. That would give us some square symmetric matrix. We'd find the eigenvalues, lambda, and then we'd find the singular values, which are just the square roots, right? So that's ultimately how you do that one. The Gram-Schmidt process one, remember, we would just follow that formula and just make sure we're not making any algebra mistakes. There's not anything too tricky that can come up with that. Here's one. Let A be a 5x17 matrix with rank 4. What is the dimension of the null space of A? So what theorem should you kind of have in mind when it tells you something about the rank and it's asking something about the null space? What theorem is that?
Is that the rank plus nullity equals n?
Yeah, exactly. It's called the rank theorem, and essentially what it says is the rank of A plus the nullity of A is equal to n, okay? And then keep in mind that the nullity is just the dimension of the null space of A, okay? So if we...
columns, right?
Yeah, n is the number of columns. So the rank is 4, the nullity is what we're looking for, the dimension of null A, and n is just the number of columns, so that's 17. So therefore the dimension of the null space of A is just 13. Greater than 4, okay. Okay. And I mean, if you were to sort of draw out the matrix, right? You've got this matrix, it's a 5 by 17. It's rank 4, so you know you've got like 4 pivots. And so that means you have to have 13. You know, you've got 4 pivot columns. That means you have to have 13 non-pivot columns or free variable columns, okay? Problem 6, I'm going to skip. That's not super relevant. Here's a good one. Let T be the linear transformation that reflects the vector X across the y-axis. What is the standard matrix of T? Okay, so this is a good practice one for remember finding standard matrices. So suppose we have our linear transformation. What the thing is saying is we look at the y-axis, and our transformation is going to take vectors and it's going to reflect them through the y-axis. So remember, reflection, the way that I think of it is if I'm reflecting along the y-axis, it's kind of like I'm taking vectors in the plane, and I'm going to fold my page over along the y-axis. That's my reflection line. And if I fold the page over, you know, if I imagine my vectors were made out of red paint or something like that, and I folded it over, if the paint was still wet, it would leave sort of a stamp on the other side. That stamp is sort of the vector that's been reflected, okay? So that's kind of geometrically what the transformation is doing. Now remember, in order to find the standard matrix for a transformation is just, I take my transformation, I plug in 1, 0. That's going to be my first column. And then I plug in 0, 1. That's going to be my second column, okay? So looking at 1, 0, when I reflect in the plane, or when I reflect in the line, I'm going to get exactly this vector here. This is T of 1, 0, which is just negative 1, 0, okay? So that tells me that the first column of my matrix is just going to be negative 1, 0. Now the second column of my matrix is just going to be whatever happens to this vector here, 0, 1. But when I reflect it in the line, what happens? It just stays put. So T of 0, 1 is just 0, 1. So therefore my second column is 0, 1. Okay? And if I look at this list, I get negative 1, 0, and 0, 1, which I think is the last option. Okay? Any questions on that one there?
So do we always, I guess, do the first column is like the x-axis and the second column is the y?
Yeah, it's always the 1, 0 tells me sort of where the first vector, you know, I always sort of look at this vector here sort of tells me, I look at where this vector goes, and wherever that vector goes, that's the first column. And then I look at this vector, and wherever that vector goes, that's the second column.
Thanks.
Awesome. Okay. I'm going to skip question 8 because it's just like a definition, and it's not even a particularly important definition. It's not super conceptual. Okay. Question 9. If A inverse is equal to A transpose, then the matrix A is always what? Well, what word do we have for a matrix whose inverse is equal to its transpose?
Orthogonal?
Yeah, it's orthogonal. Okay, so we're looking for what A has to be. What is A always? Well, I mean, A can't be the zero matrix. A could be the identity matrix, but it doesn't have to be the identity matrix. So it could be the identity matrix, but it's not necessarily. The matrix has to be an orthogonal matrix. That's kind of the definition. It doesn't have to be symmetric. It doesn't have to be triangular. Does it have to be square?
Yes.
Yeah, it does have to be a square matrix, or else inverses don't really make sense. Does it have to be a diagonal matrix? It could be, but it doesn't have to be, right? I mean, it could be the matrix 1, 0, 0, 0, negative 1, 0, 0, 0, negative 1. That could be a possibility, but it doesn't have to be. Does it have to be invertible?
Yes.
Yes, has to be invertible. Okay. Questions there? All right. Okay. Let's try and power through just a couple more here quickly. So problem 10, let u1, u2 be these vectors and let y be this vector. Let's find the coordinates of y relative to the basis u1 and u2, okay? So remember, when we ask you to find coordinates, what we're asking you to do is we're asking you to find the scalars c1 and c2 so that you can express the vector y as a linear combination of u1 and u2, okay? So in other words, we're asking for these coefficients here, okay? These are the coordinates of the vector y with respect to the basis u. Now fortunately, we have a nice formula. If you notice, if this were sort of the olden days, if this were midterm 1 and you didn't know anything about orthogonality, the way you would solve this is you would set up the matrix, the augmented matrix u1, u2 with a y here in the augmented column, and you would find the solution to this system, okay? However, if you notice that u1 and u2 are orthogonal to each other, okay? So our basis is an orthogonal basis, and if that's true, if your basis is an orthogonal basis, then you actually have a shortcut formula you can use. Okay, the first coefficient is just going to be given by y.u1 over u1.u1, and the second coefficient is just y.u2 over u2.u2. Okay, is everyone okay on that? So if your basis is orthogonal, you can use this formula here. If it's not orthogonal, then you have to sort of just set up a matrix like that. Now in this case, if we do this, our coefficient C1 is going to be 8 over 2, so it's 4. And our coefficient C2 is going to be negative 2 over 2, so it's negative 1. So 4 and negative 1, and it looks like that's the third option there. Okay. Questions there? No? All right. Let A be a square matrix with eigenvalue lambda and corresponding eigenvector x. Which of the following must be true? 2x is an eigenvector of A with eigenvalue 2 lambda. So the first option is false. 2x is, so if x is an eigenvector, then 2x will also be an eigenvector, but it's going to be an eigenvector for the same eigenvalue and not for like 2 times lambda. So if this first one had said 2x is an eigenvector of A with eigenvalue lambda, it would be correct, but it's not, okay, because it says 2 lambda. Lambda is an eigenvalue of A transpose. Is that going to be true? Yeah, that is true. Lambda can't be equal to 0. Can an eigenvalue be equal to 0? Sure can, right? So this one is false because lambda certainly could be equal to 0. A cubed times x equals lambda cubed times x. That is true. We saw an example kind of like that when we did the a to the 1001 times x. That's kind of what happened there. And then the last one, x is in the null space of A minus lambda I. Yeah. So that is true. Okay. And that kind of comes down to, remember, you know, if x is an eigenvector, then this equation is satisfied. But what you can do is you can kind of rearrange this equation to give you the following. The door just opened. Hey, buddy. Uh-oh. I got it. Here, let me throw this back up to you. Yeah. I just nailed him in the head with a big stuffed animal. That was accidental. I didn't mean to do that, but he dropped his stuffed animal. So you can rearrange this equation to basically give this equation. Okay. And if this equation is true, then it's in the null space of that matrix. Okay.
Isn't it also true because we derived x by solving for the null space of A minus lambda I?
Yeah, that's exactly how we find x. Yeah. All right, so the next question is, which of the following matrices are orthogonally diagonalizable? Well, remember, that's just the same thing as checking which of them are symmetric, so that's kind of an easy one to do. Question 13 is just a characteristic polynomial. 14 is maybe the last conceptual question. Maybe actually, you know what, I do have to run. So this question here is asking whether, it's basically saying, suppose we have a matrix which is orthogonally diagonalizable. That's kind of what the first sentence is saying. And then it's asking you which of the following have to be true. And remember, matrices that are orthogonally diagonalizable have to be symmetric. They don't have to have distinct eigenvalues. This one here is true because you can always find orthonormal eigenvectors. Q is, that's true, and this is true because they're similar. Anyways, so I kind of rushed through the end there, but I do have an appointment with someone there. So hopefully this has helped. Remember, the exam opens up tonight at 12:01 a.m. So you can start tonight. You have all the way until Wednesday night at 11:59 p.m. You have 5 hours to do it. That 5 hour window has to fit within the hours or within the time parameters I've set. So if you start at 11:30 on Wednesday night, you're only gonna have half an hour to do it. I will send out one email tonight just with some, like, not hints on the exam, but just some things to be aware of, like how to input your answers, sort of check your work, just some sort of simple reminders like that. So well, good luck on the exam. Happy studying, and remember, I'll have office hours this week, so feel free to drop by on Zoom, and we'll stay in touch. So, or if you have questions, put them on Piazza. Email me, email Haley, email the other TAs. We're all here to help. So, have a good day, and we'll good luck with all your other exams too.
Thank you.
Okay. Thank you. We'll see y'all.